So in this video, we're going to prove the fundamental theorem of calculus, part 2. So let f be continuous on the closed interval a to b, and let capital F be any antiderivative of little f here, that the function is continuous on closed interval a to b. Then the definite integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. So what we're saying here is that the definite integral from a to b of f of x dx is equal to the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit of the integral. Pretty cool. So let's do a little proof of this. In every proof, we always start with the assumptions. So I'm going to assume that f is continuous on the closed interval and that capital F is any antiderivative of little f. Now, I'm going to let a equal x1, okay? I'm going to let b equal all the way out to xm plus 1. So the first x value at a and the last x value at x sub n plus 1. So I have my interval cut up with all these little x values in between, okay? So I guess xi, and then this is like xn, and then this last one is xn plus 1. That first one is x1, okay? So we partition the interval, the closed interval from a to b, where f is continuous on that interval, into that particular partition there. And so what does that tell me? The partition f of b minus f of a, we're going to rewrite this in a clever way that incorporates all these values. This is going to be defined as f of b, which is f of x to the, or sub n plus 1, right? And then minus f of x1. Remember, x1 was equal to a, so that's a there, so we're still good. So technically, we still have the same thing, f of b minus f of a way over here. Now I'm just going to add a lot of stuff in here that's all going to cancel each other out. So what am I going to add? I'm going to add lots of parentheses and dot dot dots for infinitely many parentheses, or as many as I want in there in between. So like I said, I still have the same thing. Everything's equal. Now everything else that I add in here is going to cancel in the dot dot dots. And then like that. Okay, so all those terms are just going to cancel each other out. So this would be like I'm adding a lot of zeros. So these two cancel. And then this cancels within the dot dot dots. This cancels in the dot dot dots. And then these two cancel each other here. Okay, why is this important? Look, I'm starting at xn plus 1. I'm incorporating xn. I'm incorporating xn minus 1 all the way in the dot dot dots. And then I have x3 canceling in the dot dot dots. I have x2's canceling, and then my last one, my x1. So I got everything in my partition here. Okay, so I'm going to rewrite this. Instead of having to write all that out and then the dot dot dots, I'm going to rewrite it as a sum from k equal 1 to n. So the lowest one I have is a 1, and then I have to have f of k x sub 2 minus f of x sub 1. So that means I'm going to have something in the form f of x sub k plus 1. Okay, that way, like if I plug in a 1 here, that gets me x2 here, minus, and then f of x1 there, because k starts at 1. Okay, so that's my first one that's right there. When I bump it up to k equal to 2, that's going to be this next term here. When k equals 2, I plug in a 3 here and a 2 there, right? And then I keep going all the way until I get to that nth term where I plug in n here and n plus 1 for that part there. Okay, so this works for all of my values. So it's a sum from 1 to n. Now, why is this important? This, my friends, is equal to the derivative of the antiderivative evaluated at some k, ck, between xk and xk plus 1 in that k interval there, and multiplied by the delta x, that width in the interval. Now, why is this equal to this here? This comes from the mean value theorem. So let's think back to the mean value theorem for a second. With the mean value theorem, say we have some interval with an xk, and then I evaluate xk at capital F of xk, and then some xk plus 1, so the next x value we pick over, and then I plug it in here, and it outputs a fk plus 1 here. Now, the slope of the secant line, how is this represented? So this is y2 minus y1, so f of xk plus 1 minus f of xk, all over what? y2 minus y1 over x2 minus x1, x sub k plus 1 minus xk, right? And so what does this equal? Well, from the mean value theorem, we know that there's some k, ck in between, where if I do the derivative evaluated at that ck, it has the exact same slope. So this is equal to f prime of ck. So that f prime of ck is right here, but I also multiply both sides by this so that I can solve, because remember, I originally wanted to get this by itself, right? So I multiply both sides by this so that I can get that by itself, and now I have this by itself. Okay, so that's what's going on there. That's how we get from the green to the yellow. Mean value theorem, we could not do integration without the mean value theorem and to get us the fundamental theorem of calculus. So like I said, when we cover the mean value theorem, that's a huge theorem, very important for us. We couldn't do the last third of calculus 1 without the mean value theorem. So we evaluate that ck is some k, there's some k that exists, and that's what the mean value theorem guarantees. There's some k, ck, between xk and xk plus 1, such that when I evaluate the derivative of the antiderivative at that value, it has the same slope as the secant line slope. Okay. Now, what do I know? I know that f, capital F, is an antiderivative of little f. So when I take the derivative of capital F, I get the little f. Okay, that's all I know. The derivative of capital F is little f. The derivative of the antiderivative is the function itself. Okay. And then I replace my delta xk, my x sub k plus 1 minus xk. This width here for the kth interval is that delta x here. Okay? So these two things hold true. That's why we can say this is the same as this here. Now, what do I know? This, okay, I shouldn't have the equal sign there, but this right here, if I take the limit as n goes to infinity here, now I'm taking not just some, n equal to 50 rectangles. I'm saying I have infinitely many rectangles here. What did we learn in another video? We learned that was actually equal to the definite integral from a to b of f of x dx. Okay, that theorem 532 in your textbook, where it relates the definite integral and the limit of the Riemann sum. Okay, and then what do I know? If this is equal here, then that means this is equal here. Okay, because this is not dependent on the limit as n goes to infinity. So this is still, so the limit as n goes to infinity of capital F of B minus capital F of A is still capital F of B minus capital F of A. It's just taking the limit of a constant, right? And so this is equal to integral from A to B f of x dx there, all right? So we have just proved through limits and the mean value theorem and a clever way of rewriting f of b minus f of a that the fundamental theorem of calculus part 2 is actually true.